constitutive artificial neural networks. We have constitutive laws in continuum mechanics. And what does it mean actually? Well, basically, in very simple words, you have stress and stretch data. So you have a couple of points in the stress stretch space, and that can be a uniaxial experiment, but it can also be a higher dimensional data. And then you have to develop a constitutive law. That means you have to develop an equation that tells you, okay, what function can basically connect these scattered data points that you have. And of course, I mean, it's pretty simple. You can basically manually draw a line that somehow interpolates, but the problem is then you can do it in different ways, right? I mean, you can do it this way, or you can do it that way, or you can even do it in a very different way. So there are many ways, and it's not so simple to say what is the best way. And in fact, constitutive laws is something that can keep humans busy for decades if you have a complex material. I will come to that later when it's about arteries, and we will see constitutive laws. It's not just work for a year, it can be work for decades if you have a complex material. And so the idea is, how can you automate the process of finding constitutive laws? And so one of the ways how you can do that is you do it by machine learning. And we developed a tailor-made machine learning architecture to do the job, and we are calling them Constitutive Artificial Neural Networks. And let me explain a bit the theory. So as you all know, computer vision was somehow revolutionized by CNNs, by convolutional neural networks. And I think the big thing about CNNs is they have an architecture that is tailor-made to process visual data. This is, I think, the big deal about CNNs. And so the question is, if we want to deal with data from material science, the question is, what is an architecture tailor-made for modeling the mechanical behavior of materials? And this is what we tried to develop when we developed constitutive artificial neural networks. We aimed at developing a sort of material science counterpart of the CNNs. So a very specialized network that can do the optimal job for any kind of material and discover and develop constitutive laws in an automated manner. And so basically, we didn't want to constrain generality. So that was, there was no loss of generality that we wanted to accept. So basically, we wanted to go to the very basic foundations of theory of materials. And this is basically symmetry groups. So if you have an elastic material, you have a strain energy function psi that depends on the Cauchy-Green deformation tensor C. Then the first derivative with respect to C gives you the stress, and the second one gives you the stiffness, as you all may know. And then what we know is you can define symmetry groups. So what you see here in this center line here in the equation, you see you can require that psi of C equals psi of C, and then transformed with Q and Q transposed. And if this holds true, you basically have a strain energy function that satisfies some sort of symmetry criterion. And what sort of symmetry criterion that is depends on Q. So if you formulate Q appropriately, you can capture any kind of symmetry that way. And now the thing is, there has been a whole lot of work in the area of theory of materials, what you can do with Q and how to do this in a smart manner. And the best way, it turns out, is that you base Q on so-called structure tensors by the two equations that you see below. These structure tensors are basically tensor products of a so-called preferred direction Lj with itself. So basically you define a certain number of preferred directions, and these preferred directions give you structure tensors, and the structure tensors give you, can help you to define symmetry groups. And the interesting thing is all these thoughts are completely general. It's not only for one specific material, it holds for any material. So this holds basically both for isotropic and anisotropic materials. This holds also for practically any kind of anisotropic materials if you define Q properly. So just making the assumption that this is the mathematical structure underlying to our constitutive model is not really a loss of generality. It is only exploiting what mathematics and theoretical mechanics has yielded us over the last decades. Now, a very interesting thing is now when it comes to anisotropic materials, to nonlinear anisotropic materials, you can base your whole work on so-called generalized invariants. So when it's about isotropic materials, it's very simple. So you have the trace of C and you have the determinant of C, and then you have also a second invariant that is kind of a combination of the trace with some more complications. But in the end, so when you have anisotropic materials, you do not only have 3 invariants, you have a number of n invariants. But if n is large enough, you can basically capture any kind of strain energy function as a function of only these invariants. And so this is the whole idea of capturing general nonlinear anisotropic material behavior without any loss of generality. And so once one has understood that, one understands that learning the constitutive behavior of a general nonlinear anisotropic material does not really mean learning the relation between a deformation tensor or a strain tensor on the one hand and a stress tensor on the other hand, but rather it means only, if it's an elastic material of whatever kind, it only means we have to learn a function that maps these scalar invariants that you see here to a scalar strain energy. And that reduces the functional space vastly. So this is some more theory. So basically, this theory of generalized invariants has been worked out over the last, I would say, 20 years approximately. So Ogden and Holzapfel have made very famous contributions in this area, but also Itzkov, Ariad, and many other people. So it's a very complex theory, but also a very nice and very general theory. You can imagine, so these symmetry groups, you can illustrate them in a very, and understand them in a very simple geometric way, for example, by here a sphere or an ellipsoid and so on. So there is a whole lot of mathematics behind it. And in the end, it's very nice and very easy to interpret geometrically. Now, the general idea of CANs is now we don't learn a relation between a strain C and a stress S, but rather we learn a relation between generalized invariants of C, which are only scalars, and a strain energy psi of C, which is also only a scalar. And that is a vast reduction of the functional space. And that means we need way less training data compared to a case where we would try really to learn a tensorial relationship. So CANs incorporate substantial prior knowledge from the theory of materials to reduce the amount of training data required. And the prior knowledge that we incorporate here, interestingly, does not imply any significant prior assumption about the material. So I repeat it once again, practically any nonlinear anisotropic material can be formulated in that sense if you choose the symmetry groups appropriately. And that's just, let's say, a mathematical game to choose the symmetry groups properly. Now, this is about the theoretical background. So this is the architecture that we published around a year ago of the CANs. So basically, they are artificial neural networks that learn the connections between the scalar invariants and the strain energy functions. And they can also learn the so-called preferred directions that ultimately lead to these generalized invariants. So it's basically a sort of physics-informed machine learning in the sense that we have neural networks connecting certain parts of our architecture, but then we also have a certain physical structure. So it's not just simply a dense feed-forward neural network, but rather the physics behind it is kind of included in the way how certain neurons are connected with each other in this network. And these CANs actually can do a fantastic job when it comes to discover constitutive relations. So for example, here we tried it for trailorless data. So that's kind of, I think, famous data already, I think, from the 1940s, because it turned out that for humans back then, it was really hard to find a constitutive function that could fit these data. And actually our CANs could learn it from just around 30 data points. They could basically learn the Mooney-Rivlin constitutive law within just minutes and without any human interaction. So basically, 30 data points, that would also approximately be the amount that a human would need to learn something like the Mooney-Rivlin constitutive law, and our CANs did not need any more data and also not any human interaction. So basically, they can completely automate the job of learning the constitutive behavior of a material and even of a very complex anisotropic material. And the interesting thing is, as they incorporate substantial prior knowledge, they're very robust against noise. So this is what you see here on the right-hand side. If your data is noisy, they have not any problem actually. They've also excellent extrapolation beyond the data. So this is also what typically human-made constitutive laws have as an advantage compared to pure data-driven approaches, that pure data-driven approaches often do not extrapolate well, and let's say closed form analytical equations developed by humans do, but in fact cans also do. So they have the same favorable properties as constitutive laws developed by humans. They are robust against noise and they extrapolate well. They're also very easy to implement. So what you see here is also some tests that we have run in Abacus, which is a standard commercial finite element software, one of the ones that is most used in the industry. And it turned out really pretty simple to implement it in Abacus. You can plug it into practically any finite element code. So cans can learn the mechanical behavior of a material from similarly small amount of data as human researchers, but in a fully automatic manner.
Professor, I think we have a question from the audience.
Sure.
Yeah, thank you. Christian, this is Nat Trest from Sandia. So for the architecture you're learning a strain energy. Can you make a comment on how, is that because of your application interests, or is this something, is it possible to generalize this to elastoplasticity?
Yeah, it's pretty easy to generalize to, so we started only with hyperelastic materials because that's, I would say, a simple starting point, but we have already a fairly advanced version of the cans running for viscoelastic materials. So basically it includes an inelastic part of the deformation, and from that it's only a relatively small step to plasticity. So the ideas behind the cans can be very easily generalized, and I think that's a big advantage because some data-driven approaches to constitutive modeling are really hard to generalize to inelastic behavior, but cans are not. So cans don't have any problem with inelasticity, plasticity, or whatsoever.
And it's the same, there are closed form expressions for the invariances and the same.
Yeah, it's of course, I mean, it's a bit of a different story. So for example, when it comes to viscoelasticity, that's something that we're going to publish probably over the next month. So we are running at the moment the last test. So there again, you need to think about what the theory of materials can really tell you. And when it comes to viscoelasticity, it's all about thermodynamic consistency. Then when it comes to plasticity, it's also about thermodynamic consistency, but also about the shape of the yield surface. So again, so it's not as simple as for the hyperelastic materials. And this is also the reason why we did not publish all this in a single paper, elasticity, viscoelasticity, and plasticity, because at each time a slightly different story. So you have really to make, you have really to sit down and think again. It's not a trivial extension, but it's a possible extension. But it's something that each deserves its own paper, and it takes a while to work it out in detail properly. It's not that you can take the cans that I'm presenting here and then just within 5 minutes develop an extension for plasticity. It's not as simple as that, but if you sit down and work for a while on it, it's definitely possible, and we are already halfway done in that direction.
Christian, I have since we interrupted you here. So Charbel Farhad who is working with me in our Muri project, is developing a similar type of structure preserving, but he doesn't use the generalized invariance. But he has like these 7 principles, monotonicity, and a list of properties that the constitutive law has to satisfy. And he then puts constraints on it, and he gets also really good results. Now, for example, do you using the invariant, do you automatically satisfy these other constraints? I don't know if you've seen his work, but we can tell you what 7 principles he's using.
So I can imagine what it is, right? I mean, there's probably polyconvexity, there's monotonicity, there are a couple of,
yes, exactly.
So the thing is, on purpose, we did not include these because they are not strict requirements for any material. We wanted to stay general. So we know that many engineering materials typically satisfy properties like monotonicity or polyconvexity, but in fact, it's not a must, right? There can be materials that don't do that. And so if you start with these constraints, you may do pretty well for standard rubber materials, or actually for many reasonable materials. But if you have very complex architected materials, you may have actually behavior that is on purpose violating these constraints. So we did not want to develop an architecture that imposes any constraints that are beyond the most basic physical requirements, and neither monotonicity nor polyconvexity nor many other of these things are really must-haves. It's rather you will most likely have them because many reasonable materials will have them, but not every material. And so we did neglect them on purpose because we wanted to stay more general. And we did find out, I mean, we also tested these things, of course, and we did find out that adding these constraints does not really help us, because if your material satisfies things like monotonicity or polyconvexity in its behavior, the cans will learn it already from the relatively weak constraints of the generalized invariants. These are already constraining enough. But if your material does not satisfy these constraints, then you actually would prevent the cans from learning the true behavior. So we did not include these more advanced constraints because they are not always satisfied by every material, and we didn't, so we wanted to stay general.
Okay, thank you.
So yeah, but thank you for these interesting questions. Now, yeah, I'm done with the cans. Now, we're coming to the next part, which is constitutive laws for arteries. So the history of constitutive modeling of arteries is actually really, I think, a very long story. So if you go back, you find already papers in the 1970s. So probably Jay Humphrey knows this all much better than I do. So Jay, if I make here any mistake in summarizing things, please interrupt. I'm happy to learn from you in this area. So I found papers as early as in the 1970s, and I would assume, as always in science, if you go further back, you'll always probably find somebody working on something in that direction. But then what we found, of course, was in the 1980s, you have the very famous work of Fang. So Fang developed basically this idea of an exponential strain energy function that you see here on the left-hand side printed. And then in the 1990s, this whole area basically started to gain momentum. So you have a lot of work, for example, also by Jay Humphrey here in 1995, who's among the audience, but also many other people picked up these things in the 1990s. So I think their arteries really started to become popular. And then we had this landmark paper in the then we had this landmark paper in 2000 from Holz, Apfelgasser, and Ogden, a new constitutive framework for arterial wall mechanics, where arteries are conceptualized as a two-layer thick-walled tube, and each layer is a matrix reinforced with discrete fiber families. And I think this was kind of a groundbreaking model that has been picked up by many other peoples over the last 20 years. And so basically what you can say is when it was Fang's law, it was still rather phenomenological, working on the macro scale. And then Holz-Apfel's work basically started, I would say, into the era of mesoscopic modeling. So people looked at the fact that an artery is not a homogeneous solid, but you have different layers, in fact, and a mixture of different things. And then in the 2010s, increasingly, already in the late 2000s, but then all the more in the 2010s, people started looking increasingly at the microstructure, and they said, well, it's not only 2 or 4 fiber families, it's actually stochastically distributed fibers. And for example, you have collagen fibers that are distributed in a so-called von Mises distribution, what you see here on the right-hand side. And I think this work was also fueled by the fact that ever better experimental facilities allowed us really to do imaging and to detect the fiber structure on a micro level. And yeah, now that brings us to the point, what can experiments provide in terms of data for us? So we have imaging of arteries. So state of the art is second harmonic generation imaging via multiphoton microscopy. So it's basically a sort of fluorescence imaging where you have some fluorescence light with twice the incident frequency. And you basically have contrast in these images from a material-specific ability to second harmonic generation. So collagen does not have the same as elastin or cells and so on. So that's how you get the contrast in these images, and you get a really superior resolution on the microscale. So I'm showing you here on the right-hand side 2 pictures which are cited from papers from Holz-Apfel 2016 and one from the group of Jay Humphrey and Cristina Cavinato, a postdoc of Jay Humphrey from 2021. So these are basically images that you can get nowadays to get more information about the true microstructure of arteries. And then what you have in addition to this imaging is histological analysis. So what you can do is optical light microscopy. Again, here it's an image from a paper of the group of Gerhard Holz-Apfel in Graz. You can basically see there the different layers of your artery, and you can also see the mass fractions when you're doing staining. You can see the mass fractions within the different layers. So you can roughly determine how much collagen do you have, how much elastin, how much smooth muscle cells, what's the volume fraction, for example, of your cells, of your cell nuclei, and so on. So that provides you a whole lot of data. And then you also have mechanical testing. So things started with the very simple uniaxial and biaxial tests, where you see here on the right-hand side pictures from the group of Markus Böhl in Braunschweig. So that's a classical uniaxial soft tissue test, and here a biaxial soft tissue test. These tests are easy to perform, and they impose a nearly homogeneous deformation field on the sample, at least in the center, not close to the edges, but in the center at least, in a good approximation. Then there's the more sophisticated way of doing mechanical testing, which is inflation testing. So, for example, Jay Humphrey in his lab at Yale has, I think, very sophisticated facilities for these things. So you take an artery and you suture it to these cannulae here on the left and right-hand side, and then you increase the pressure in the artery. And then you basically get a biaxial deformation state that you can trace via optical tracking. And that's relatively simple and similar to what you actually have in vivo in an artery. So that's the advantage. It's a very realistic way of doing mechanical testing of arterial tissue. So yeah, what you can get in short is you have the fibrous microstructure in terms of orientation distributions, you have mass fractions, and you have stress strain data. This is what modern experiments can provide you in a very high quality. And now, basically, these are the data we have. And what we have seen is, I mean, I've shown you, people started working on constitutive laws for arteries already in the 1970s, 1980s. So basically, that was 40 to 50 years ago. So what we can see is, and there's still plenty of groups around the world working on it. So developing a constitutive law for a complex material like an artery, that can really be a life's work. It can be a job for a whole researcher's life or even beyond. Now, the questions that have been driving Kevin and me and our collaborators was, how can we accelerate the development of such constitutive laws by machine learning, for example, using the CANs? And then also, how can we move on to predictive modeling? Because although people have been working now for 40 to 50 years on constitutive modeling of arteries, the modeling is still descriptive. So you provide stress strain data, and then people can give you a constitutive relation that can kind of describe this behavior. It can fit the data, but it cannot predict you. If you arrive with an unknown sample, let's say, but with a known microstructure, it would be hard for the current constitutive relations to predict to you what this unknown sample has as a macroscopic mechanical behavior. And so that was also one of our motivations. We really wanted to do the important step from descriptive modeling, which is the current state of the art, towards predictive modeling, which is at the moment still not yet possible with the standard methods. And yeah, about what we did in that area with the data from the group of Gerhard Holzapfel and Graz and the group of Jay Humphrey at Yale University, this is something that Kevin is now going to show you over the next minutes. I stop now sharing screen and Kevin will continue.
Okay, thank you, Christian, for handling over. Try to get the okay, so yeah, I will speak about our machine learning models where we try to, exactly like Christian outlined already, to model the artery tissue behavior. And this is two-parted. In the first part, I would like to show you a study that we have done together with a group of Gerhard Holzapfel, where we try to learn material parameters for microstructural data. And in the second part, I'm going to show you our collaboration together with Jay Humphrey's group at Yale, where we try to learn from the microstructure directly the functional relationships from scratch. So in the first study, what we've done together with the group of Gerhard Holzapfel, who delivered here all the data, were that we had 27 human aortic tissue samples which you can see here on the right-hand side for the collagen microstructures that were obtained from second harmonic generation images. And what you can see here is on the y-axis the depth of the tissue samples, and on the x-axis you see the fiber angle, and color-coded is here the relatively fiber presence in the tissue samples. In addition to that, we had the mass fractions given from classical histology of collagen, smooth muscle cells, and elastin. And we referenced those data to the mechanics, which were given here by stress strain curves from uniaxial tension tests in both axial and circumferential direction, such that we could identify here the tissue anisotropy, which is mainly due to here the different collagen fiber architectures. We had here only 27 samples, and this is quite small data. If you would like to learn from that, the biomechanical relations for such complex tissues. And even worse was that it was human samples, because that means you cannot really select the age group or the health that you wanted to obtain for you can get. And this is then here displayed by a considerably head. And we tried here to visualize this by this latent space plot, where here every point now indicate one set of material parameters that we have obtained by classical material parameter fitting with respect here to the well-established constitutive model holds up in 2015. And here you can see the material parameters and here on the y-axis corresponds to the material parameters of the model, and C here, which is the color code, is the material parameter of the isotropic ground matrix. But I also will in detail explain this model on the next slide. But how we tackled this now in order to overcome this problem with the huge heterogeneity was that we first of all confined here the space by a subset, which you can see here indicated by this black ellipse. And this is now centered here around this red cross, which is indicating the medium parameter set of all data that you can see displayed here. So we really only focused on this subset because of the property of neural network models or machine models in general, that they are really good. The space here gets a bit more or less densely sampled. And what we also did here in order to overcome the problem with this huge heterogeneity and the complex data was that we only try here really to learn the material parameter of a well-established constitutive model instead of directly learning the functional relationships. And we make a use of the Holzapfel model of 2015. And this is basically a model where the strain energy is split into two parts, which is quite often the case for soft tissues, where you have the first part corresponds to the strain energy of the ground matrix with respect to the first invariant. And the second part is here the anisotropic contribution with the two preferred fiber directions here indicated by E4 and E6. And the isotropic part is here given by the Neo-Hookean model, while the anisotropic part is given by this exponential type of model, which is already known from Fang. The only difference is here that we use here this generalized invariance. And they are, I will come to that in a second, then based on the structure. And altogether, we have here exactly these three material parameters, C, K1, K2, which you also could see on the previous slide for the visualization of this latent space.
Kevin, I have a question. So you have 27 data points. Do you do any data augmentation methods?
Yeah,
What kind of?
So we do we did classical shuffling the
Sorry, I think you're buffering. It's hard to
and somehow randomly rotating them and translating them.
Okay.
Oh. Yeah, sorry.
So Kevin,
don't-
maybe
it
perhaps
better
the
now?
internet
Okay.
connection is a bit poor, the transatlantic one. So maybe if you can switch off your camera, perhaps that might help.
It was good with you, Christian. It was good, but I think where he is, he's
Yeah,
connected.
yeah. Okay, so maybe Kevin,
Christian,
switch off your
would
camera. Or
Otherwise,
I think that
also
will help.
Christian,
Let's
Okay.
continue and see whether this works.
otherwise you can take over if you want or something. So yes, we I don't know whether this came through or came across, but we tried or we did data augmentation by randomly shuffling and translating pixel-wise the raw image data. Yeah, this helped a bit, but it was still not sufficient in order to really learn functional relationships out of the data. Yeah. Okay, so this was this was the material parameters here for the strain energy function, and what we in addition included here were now the fiber dispersion, which is here captured by the structural tensor in terms, first of all, in the fiber dispersion in the in-plane direction, which is indicated here on the left-hand side on the image, and then which was figured out in the 2015 model version, that you also have another kind of collagen fiber dispersion in the off-plane direction, and this is here captured by this surface normal unit vector MN. And by this, you can then compute the generalized invariance, which are then here entered in the model, and you get this in terms of two dispersion parameters. You have here kappa off-plane and kappa in-plane, and so altogether we had three structural parameters to describe here the network architecture. This were alpha, which is the mean direction of the preferred fiber alignment, which you can see here in the plane view, and the two dispersion parameters for the collagen concentration around the mean directions. So, and our architecture then looked the following the deep learning architecture. So we really tried here with this deep learning block to identify this material parameters, which I've just outlined, C, K1, K2, based on the second harmonic generation images, and here a residual network architecture in conjunction with the volume fractions that we obtained from classical light microscopy, and try or combine that here with this classical feed-forward dense layers in order to predict then the material parameter set, which were then put here into the constitutive model, which I've just outlined, while the structural parameters we could directly obtain as a post-processing step from the microscopical data. And yeah, then together with the stretch, we obtained then the stress response we used then to train the model parameters. We had a classical training.
Hi, Kevin. This is Minglang from Brown. I have a quick question. Could you go back to your previous slide? Yeah, so here, why you take the mass fraction as the input of the dense layer instead of putting it directly at your constitutive model?
Because the constitutive model, like I've outlined it before, which is well established, has a direct definition to take into account the volume fractions.
Oh,
because it's rather yeah. So
okay.
we try to use this as an additional information in order to predict then the sample specific material parameter set. Yeah.
Thank you.
Sure. So the training and validation scheme was quite common scheme we used here because of our small data, a leave one out cross validation. The only difference that we had here were that we used for our test sample. So the test sample was used here to define the stopping criterion in order to have here a really representative sample in view of our validation sample. We used here a criterion, which was that we choose it based on the smallest distance of the median parameter set of our training data. And then we run this in 6 iterations. 6 was here because this was exactly the samples which you have seen in the very beginning defined of this subset that we only consider in order to get predictive. And we referenced it and compared that with the classical fitting protocol. So we really did classical parameter fitting with respect to our tissue sample data, mechanical data, and then just take the median data set of the training data and use then this parameter set then for the validation data and compare this against our deep learning model. And this is the results that you can see here. So we have a black solid line is the model response of our deep learning model in comparison to the circles, which are the experimental data, and the blue dashed line is here the model response of the classical fitting model. And we obtain here a really high predictive accuracy in terms of R squared, which was 0.97 for the deep learning model, while in contrast, it was about 0.67 for the standard fitting model. So the deep learning model really here improved, even though it was only of the subset of this 6 different data or different tissue samples. Okay, with this, I come to part B, where we learned the functional relationships. And this was, like Christian already outlined, the work together with Cristina Cabinato and Jay Humphrey from Yale University. And here we had exactly the setup, which is mainly the work of Cristina and Jay Humphrey with these inflation tests, where we really could, or really had here the data based on inflating the artery samples of the mice. And this is, of course, especially nice because you somehow can mimic a equivalent or in vivo equivalent loading condition. And during that, you can also non-destructively somehow measure the microstructural data by the microscopical setup here, so that we had here the information about collagen, elastin, and the cells, and could reference this to the mechanical data optically obtained by the stresses and associated stretches in the axial and circumferential direction. And even though we still had small data here, like it was 25, so even 2 less than in the previous study, we have, of course, due to the mice sample here, a much lower heterogeneity across the different tissue samples, even though in total we considered here 5 different age groups of the mice samples. Yeah, like I outlined before, we obtained here the microstructural parameters again by multiphotonic microscopy at different length scales in order to identify the different constituents. And I think what also was here a huge benefit is that we didn't had to learn the material descriptors from the raw image data like you have seen in the previous study, but here we really made use of Christina's post-processing scripts where she really could identify meaningful mechanical descriptors of the material. Like for instance, what you can see here with this yellowish line, this was for instance, the collagen waviness. And so we had really meaningful microstructural parameters that we could feed into the neural network architecture. And this we did with the CAN architecture, which was already introduced by Christian.
Sorry to interrupt, Kevin. Can I ask a question about the previous slide?
Yeah.
Are there other modalities available other than this in terms of, so in like metal additive material science, we're doing some similar work and we look at like XRD and XRF and all these other things. Are there other measurements that could be collected? Is it just you chose to go with this single type of measurement?
This is really not my domain of expertise. Actually, this I would handle over the question rather to Christina or Jay Humphrey. We obtained this data just from them, and I think this is, yeah, from the best of my understanding, really state-of-the-art microstructural parameters in order to investigate the tissue.
Yeah, Nat, this is Jay Humphrey, and what Kevin just said is true. When you think about soft tissues, there are multiple levels of imaging that can be done. The more macroscopic, you do common histology, which was shown earlier, but those are on fixed samples. The multiphoton microscopy is on non-fixed samples, so you can image under multiple loading conditions. And again, you're getting sort of fiber level information. You can also include electron microscopy, both scanning and transmission, and that gets you more to a nanoscale. So it really depends on which scale of the microstructure, to mesostructure to macrostructure that you're interested in. But multiphoton is really state of the art as far as soft tissue imaging.
And it's really giving you the full picture. Is that the correct interpretation? Like it has all the information?
No, you never get the full picture. One of the most severely lacking pieces of information is on cross-linking, both inter and intramolecular cross-linking. And there is a way to extract some of that information from the multiphoton, but it's challenging. So then you have to go to some other assays which are destructive. So I would say that's really the key thing that's missing here.
Got it. Thank you.
Great, thank you. Yeah, exactly. So we use those microstructural parameters here into the CAN architecture in order to basically learn the functional relationship between the invariance and the strain energy here. The only difference here is that we didn't have to learn the preferred fiber directions and the associated weights. We directly got them here from the post-processing scripts of Christina, so that we didn't have to learn them, but we rather could take them and directly compute here the generalized invariance that enter here the model. So training and validation was again a leave-on-out cross-validation with the 25 tissue samples here. The criterion for stopping were based on the smallest class of the test sample, and the test sample was chosen accordingly to the age group of the validation sample. So if that the test sample is really representative to the validation sample in order here to get a good stopping criterion. And you can see this here for one representative sample, where the red solid line here is the test sample where we stop the training, and on the left-hand side is then the prediction for the axial and circumferential stress response in a solid line, and the markers are here showing the experimental data. And
Kevin, can I
Sure.
how could the testing error be smaller than the training error?
I would say this is just because it was probably, I mean, it's a good question, but it's leave-on-out validation. So you only take a single sample out of the pool, and it could be just.
But how many times do you rotate every time? You do like 26 times or 24 times?
25.
25 times?
Yeah.
And that's a little suspicious. You wouldn't see that big. I mean, sometimes there's like this anomaly, but not that such a big difference, because you see the training error is decaying. Actually, you could have gone a little longer on the training. So that could be also a, but anyway, that yeah. So there's an overfitting from validation. You can see there's an overfitting there.
Yeah, exactly. But we stopped before, right?
Yeah.
But yes, but I mean, of course, leave-on-out cross-validation is never the best. Normally, you would really like to do that with a 20% and 60% probably training, that you really get here, and let's say more like an average data set and not for a single sample, I think. But since we mostly operate on such small data in biomechanics, it's sometimes tricky to get this run. Yeah. And this is now the whole picture for our prediction results. So you can see here the red points indicate the validation prediction for R squared, and color-coded are here shown the different age groups that we considered. So P21 stands here for postnatal 21 days until postnatal here 1 year. And yeah, throughout the different age groups, we have probably a good agreement or high prediction accuracy, except of here 2 outliers that you can see in the older age groups. Exactly, yeah. And so all in all, I think are good results for this small training sample size. And here are just qualitatively shown how the model predictions would qualitatively look for different age groups and the individual samples that we considered here. Okay, what we also
Kevin, can you say,
Yeah.
take one of these figures and show us what all these curves mean? Because so the blue is the CAN, right?
The solid lines are exactly. So this is the same legend as I showed here. So
Okay.
solid lines are the prediction and the markers are the experimental data.
Okay, so there's correspondence between. I think I'm missing something. That's fine. Go on, and maybe Enrui will explain to me later.
Okay. What we also have compared was the CAN model response, which I've just showed you before, which is here on the bottom row, in comparison to if we only would predict the material parameters of a well-established constitutive model. One of these well-established ones is the so-called 4-fiber family model. And here we really only used the microstructural parameters with the neural network model in order to predict the material parameters. And you can see here that even though for each individual sample, this model would actually give you a perfect fit, but if you try to combine that for all the different age groups, then it drastically reduces here the predictive capabilities compared to this more generalizable model, which you can get by learning the functional relationships with the CAN model. And another thing that we have done, we also were interested in not only, let's say, predicting the strain energy based on the microstructural parameters, but after training, we were also interested in, okay, which microstructural parameters was now results. And for that, we used so-called layer-wise relevance propagation, which is a really common tool in order to somehow, in computer vision, to explain why a certain model predicted well or on which basis is predicted well. So we applied it also here. And this is actually just fulfilling a set of conservation laws. And you have here 2 design parameters where you basically can choose how much you would like to weight the positive weighting factors against the negative ones. So we have used this here for all samples in average, that we could somehow get a quantitative feeling about which microstructural parameters had the most influence on learning the strain energy function. And here the first 3 or top 3 parameters were all associated with collagen, which also somehow gives us a good feeling, because this is very well known from literature that collagen has a really high impact on the mechanics of artery tissue or biological tissues in general, mostly. And we also applied it in order somehow to illustrate or to learn a bit more about the relevance during aging. So here, we are here depicted 4 different parameters where we could find a statistically significant increase or decrease during aging. For instance, here for the collagen volume fracture in the outer layer, the adventitia, where you can see here this increasing due to aging. And what we also tried here is just using the top 7 features in order to get we only use the top 7 features in order to retrain our model and also see whether this has a huge influence on the predictivity. And you can see here that using the top 7 features only reduced the predictive capabilities by 0.02. so really less reduction. And we also used that to only consider the top 4 features, and also this only slightly decreases the predictive capabilities. I also tested it vice versa, and it has much drastic effects on the predictivity. So also this could then somehow be used in order to, also for the clinics to say which parameters has the most impact in order to probably get a patient-specific model prediction or something like that. And this is just, again, shown here on the overview slide with the top 7 features versus the top 4 features with a reduction guided by here these layer-wise relevant propagation. Okay, with this, I would like to hand it over to Christian again.
Yeah, so let me summarize the things. What we have shown today was first the concept of constitutive artificial neural networks as a sort of tailor-made machine learning architecture for material science. It can capture nearly arbitrary nonlinear and anisotropic behavior. It incorporates prior information from materials theory, and it can therefore learn mechanical properties already from small data. So very comparable to what also a human would need to develop a theoretical closed form analytical constitutive law. The cans can excellently inter and extrapolate, which I think is also a thing that is usually only attributed with theoretical equations. And now we have it also for the machine learning equations, because previous data-driven methods to constitutive modeling had often this lack of inter and extrapolability. And then it's also robust against noise. So, and it can do predictive constitutive modeling. So this is also what we have shown. Over the last decades, we have collected, or many groups around the world have collected vast microstructural data for soft biological tissues. And using these data, cans can really learn not only to describe the mechanical properties of arterial tissue. So I think this has been the big deal of the last 20 years, describing the behavior. And I think the big deal of the 2020s for soft tissue biomechanics will really be predictive modeling, doing that important step. And cans have shown that they can do it. And of course, it's still only for a small number of samples, and there may be these or those caveats and everything. But I think we have shown that altogether that cans can do this job. And I think they have plenty of potential to do even a better job if you put in some more years of work in them to improve them and collaborate with experimental groups to get even more and better data. So that brings me to my last slide. So further reading, if you're interested to read a bit more about the things we've presented today, there are 3 articles, one about the cans in the Journal of Computational Physics, and then 2 about our work with arteries, one in Interface and one in Acta Biomaterialia. And finally, I would like to acknowledge once more Zelda Sherifova and Gerhard Holzapfel from Graz University of Technology in Austria, and Christina Cavinato and Jay Humphrey from Yale University for providing us the data and for collaborating with us and providing us also their very much appreciated advice how to use them in a good way to do machine learning for arteries. Yeah, and that's the end of my presentation. I thank you all for your attention. And if you have any questions, if we still have time left, I'm not yet sure. George, if not, please cut me off.
No, there is time. No, we don't impose strict limits here. We are freelancing.
Thank you, Professor Cyron. I think Professor Humphrey has some questions.
Yeah, Christian and Kevin, thank you both for a wonderful presentation and great work. I just want to mention one thing. It gets back a little bit to part of my comment to Nat, and that is preceding the 2000 paper by Gerhard Holzapfel and including his paper, a lot of these microstructurally motivated models or constitutive models assume that the 2 primary structural constituents in soft tissues were elastin and collagen. And we look for those, and we can look for those in 2-photon fluorescence and second harmonic generation. But the fact of the matter is soft tissues are much, much more complicated. The arterial wall includes up to 100 different structural proteins and glycoproteins and glycosaminoglycans, and we're learning more and more how mutations to the so-called lesser matrix constituents can have dramatic effects on the structural integrity of the wall or the mechanical behavior. So I think that whereas traditional constitutive equations have been sufficient in providing good descriptions of material behavior, as we enter this new phase where we can selectively knock out various proteins and glycoproteins, it's just, you know, I don't think it's possible to use traditional constitutive theories to say how do these 100 different contributors to the behavior influence our constitutive equations, and how do you account for those interactions? And you add to that physical entanglements and cross-linking. And Nat, I don't know about your work, but certainly that the same would be true in polymers, where you have so many different additives, even in elastomers. So I would just like to say both the work that's being done in Hamburg and also at Brown and at Providence, I think this is really the strength within soft tissue mechanics, that CANs, PENs, DeepONet, et cetera, will be able to help us to understand and predict how mutations to literally dozens up to hundreds of different constituents will affect the behavior, the vulnerability, the disease progression that we just simply couldn't do with traditional models. Thank you.
Maybe to add on to that question, the specific research interest we have is in high throughput measurements that you can use to complement the kind of measurements that you're discussing. So like you said, for each one of these things, you can calibrate it to this high fidelity image, but whether you can actually do that in situ for every single patient and so on is a question. So that's maybe the thing I was trying to drill down toward, is whether you view that there might be other types of complementary information that in a multi-fidelity setting, right, you could learn how to boost that and then have that be an input to your constitutive model, for example.
So for the CANs, it would not be any problem to take any sort of additional information. So I think one of the big advantages of these networks is they incorporate theoretical knowledge of some kind, but then they can add arbitrary additional knowledge. So I mean, you can even think, when it comes to synthetic materials, you can include microstructural information from different sources in a sort of sensor fusion, but you can also actually include information from processing. So when it comes, for example, to magnesium or steel alloys, you know, you can include information from the processing of these alloys, and that can also be very important because that can have effects on the microstructure that you may not directly see in your imaging modalities. So I think the CANs are a tailor-made tool also for high throughput experiments in data science. And actually, so my second affiliation is with the Helmholtz-Zentrum Herion close to Hamburg. So they are a federal research laboratory in material science. There's also a lot of high throughput experiments for different, typically engineering materials, not so much biological materials, but engineering materials. And there we see plenty of potential for these CANs, because there, when you develop new alloys, for example, new magnesium alloys or new polymers, for example, polymers are highly complex materials, and not all the information you may get from imaging. Imaging is one source, but I think very often it's rather some soft knowledge about processing parameters where you know it should affect the microstructure, but you cannot image exactly how it does. And then what you can simply do is you simply include parameters from the processing. So basically parameters that your machine can provide, metadata basically. And the CANs can also take that and fuse them with imaging data and with information from materials theory, and then give you a big picture and do predictive modeling. So I think that's one of the biggest advantages, that you are not bound to a single source of information, but can merge different sources actually.
Minglang is from watching from MIT. Ming, do you have any comments, any questions?
Yeah, I actually, it's very nice work. I have a question regarding this study. Let's say, okay, if you have learned a trained CAN network, and through, let's say, the bunch of data, then you pick, let's say, if you have a new experiment from a different patient or mice or mouse, let's say, you have the stress strain curve, then can you use your the constitutive model you learned, trying to infer back the microstructure features?
Yeah, so that's a very important question. So the big problem is it's not the big problem of homogenization or scale bridging mechanics of materials is it's not a bijection mathematically. So each microstructure has a unique determined macroscopic mechanical behavior, but for a given macromechanical behavior, there can be several possible microstructures giving the same macromechanical behavior. So mathematically speaking, it's not a bijection. So from a given macromechanical stress strain behavior, you cannot infer exactly and certainly the microstructure. But what you could do is you can infer probability distributions about rather likely or rather unlikely microstructures. And this is, I think, what CANs will be able to do in the future. We haven't done it yet, but we believe that CANs are exactly the right architecture to do that job. But yeah, only in the sense of only in a probabilistic sense. So there will be no deterministic answer because of the non-uniqueness when you go from macro to micro.
I see. That means you need more data, I guess. Some more data.
More data, yeah, more data, right? I mean, but that will be a very interesting application area. So if you if you're interested in such things, I mean, I would be happy to be in touch because I think that will be one of the most interesting things, how to do the inverse relation, right? At least in a probabilistic sense, or in the sense also of architected materials. If you have a given macroscopic behavior, what would be the ideal microstructure? And then to make the problem unique, to get some sort of bijection, you can add some optimality constraints actually. So that could all be done in the future, but it has not yet been done. So I mean, we published the CANs 1 year ago, and this is, I would say, future work.
And Rui, maybe you can tell Kevin, or if you have any comments for Christian or Kevin, or you can tell Kevin about how they can use more modern data augmentation techniques like mix-up and so on. And Rui,
yeah. To start with, actually, I have a question regarding the predictive constitutive modeling for autoarrays. If my understanding is correct, is your usage of the microstructural image for the first part, learning the parameters, it's taking the raw images, but for the second part, that's taking the microstructural parameters. Is that correct?
Yeah, Kevin, maybe you can comment on that.
Yeah, it's completely correct, right? In the first part, we try to learn this descriptors from the raw image data. In the second part, we got them by post-processing scripts of Christina.
Okay, so for the second part, does it like maybe I have missed something. In the CAN, the input includes the deformation state as well as the microstructural parameters post-processed from images. Then that gives you the prediction of the maybe stress response corresponding to that deformation state and the microstructural parameters extracted from the images.
Yeah, that's right.
Okay, got it. Yeah. Actually, regarding what George said just now, let me see. Actually, in one of my recent works, we are using some other data augmentation techniques like mix-up and other things, especially because in the work that we do, we consider constitutive modeling multiple genotypes at the same time, and we want to do some like both forward prediction, like given the genotype, predict the biomechanical properties, and the inverse thing from biomechanical properties to genotype at the same time. So for that thing, we essentially include some mix-up augmentation where we view we like linearly combine the stress strain relationship of the raw samples into some synthetic data, and use that to improve the performance of the model. Yeah, that's the additional augmentation technique that we use in our model. But because
maybe we can send the Kevin.
We would be happy if you could send us these relevant articles to Kevin and also me in copy. So we would be happy.
Yeah. Kaisi, for the interest, Kaisi also has a question. Kaisi, you raised your hand, right?
Yes. I hope I didn't use. Doesn't use.
Introduce yourself. Kaisi is Minnesota.
Yeah, I'm
We move around the world here.
Yeah, from Minnesota. So very nice talk. I have a question regarding Kevin's presentation. So for the data, it seems, or the training data is from the biaxial mechanical testing. I'm just curious about whether you also try to apply your train model to other loading pattern, such as a pure shear test.
Yeah, we did not. We haven't done it with the tested data. We have done it before in the Ken paper with synthetic data. So we tried to see which deformation state we can use to train the model and on which deformation states it would generalize. We have visualized this over the invariant plane because this gives you then, for at least for isotropic materials, a feeling about how well it can generalize, and it performed very well on this. It's a bit harder to do this actually for anisotropic materials,
Right.
because then you have a much larger state space, so to say. So there we haven't tested yet.
Okay.
Yeah, but that would be a cool thing to do actually. I agree.
Okay, thank you.
Anybody else has questions?
I have one quick question.
Yes, sure.
Yeah, so this is a song from Brown. So in the first part of Kevin's talk, I was wondering if you can also consider other type of modeling, so like the form of the constitutive law. So I saw that you only have like the exponential form. Is it possible to consider other types? And I'm in particular interested in like non-local models.
In principle, it's possible. It's probably not so straightforward to do so if you use non-local models. Haven't tested it yet, but then you would somehow, you probably couldn't do that with an analytical form of the constitutive model. You probably have to then solve it on a grid or something, if I understand your question right.
Non-local in time, non-local in time or non-local in space?
Yeah, I'm talking about the non-local in time because eventually we have the stress-strain relationship.
So that's for the viscoelastic part that they were talking
about. For the viscoelastic part of it, yes.
Yeah, so the CNN would not be the right, I mean, that's the other thing. The CNN would not be the right architecture. I think you want to change the first letter to, well, C is constitutive, but the architecture could be limited. And I was going to suggest actually that as because some data, for example, the work we're doing, Jay, she's using a DeepNet. CNN could be the branch, but you can have you can have an FNN, you can have RNN for this case, for example, for non-local in time that to get the hysteresis or non-locality. So there are one idea, Christian, maybe you can consider is to create it like an architecture which is more a universal platform, like a DeepNet that you can build multi branches and a continuous output space. Because now it's actually you are actually on a discrete output, so you're not really finding a function, you're finding a projection of a function.
Yeah, I mean, we are thinking already about such generalizations. So yeah, I mean, thank you for that suggestion. So I mean, at the moment, so I mean, first we wanted, of course, to come up with something that could be tested easily. And I mean, hyperelasticity is a very good testing case where you can easily get material data, right? But definitely, I agree, such extensions will be very much needed in the future to address a broader scope. Yeah, thank you.
Some data, I think we had a good discussion. We had a good discussion, so maybe you can thank the speakers and we move on. Thank you very much, Christian.
Thank you for the invitation, George, and thank you, Somdata, for organizing. It was a great pleasure to talk here.
Thank you.
Thank you, Professor Cyron, and thank you, Kevin, for tuning in today. And we'll move into our second speaker, who is Minglang Yin. We all know him. He's our Crunch member, and he would be talking to us about his newly published work about interfacing finite elements with deep neural operators for fast multiscale modeling of mechanics problems. And yeah, Minglang, you would want to share your screen.
Yeah, thank you.
Minglang, can I say one thing while you're setting up is that I think this is part of the special issue for the retirement of Professor Tinsley Oden that we all know here, the mechanics people, of course. And so I don't know how many articles they invited, but this is one of the invited articles.
Yeah, thank you. Can everybody see my screen?
Yes, Minglang.
Okay, yeah, thank you. Thank you. So today I would like to present our recent work on interfacing finite elements with DeepNet. So this is a joint work with Andre at Brown and Professor Yu at Lehigh University. So I'm gonna talk about, I briefly introduce a multiscale modeling and machine learning at the beginning, and then we'll take a deep dive into the model framework on how to couple DeepNet with finite elements. And then I'm gonna show 4 illustrative examples, including a static Poisson equation and dynamic heat equation, and 2 a little bit more complicated mechanical problem. So, and then I'll conclude. So multiscale modeling is widely applied in by a wide variety of research areas, including turbulence and biological sciences. So especially for those system with multi-scale features. So from a methodological perspective, so there are 2 types of multi-scale modeling. One is a sequential modeling, and the other one is concurrent modeling. So so basically you have 2 models. One is a coarse model that can be used to describe some macro scale features, and it's more cheap. And on the other hand, you have a finer model that can be used to describe some of the local or macro scale features, which is typically be very expensive. So the sequential modeling is to, the idea of sequential modeling is to perform one of the features and then extract some useful information from that, and then set up the simulation of the other model using the extracted information. And the idea of concurrent coupling is that these 2 models are coupled on the fly so that they can communicate during a simulation. And there are a lot of classical algorithms, including multi-grid methods, domain decomposition, or quasi-continuum modeling. And of course, there are several general methodologies developed by Professor Kaprikides at Johns Hopkins and Professor Wu at Princeton. But however, these types of multi-scale models, so I would say the big disadvantages of this multi-scale modeling is they are too expensive. So it's caused by the application of the microscale solver, which is very, very expensive. So in our research, we're gonna address on these issues by combining multi-scale modeling with machine learning. So here I'm showing you a vision that I copied from this paper, which published in 2019. So here they list a list of tasks that can be achieved by combining machine learning and a multi-scale coupling, and one of them is predicting system dynamics, which is one I'm going to looking at. So in this research, we'll explore the idea of multi-scale modeling with machine learning by employing a DeepNet, a neural operator, as an efficient surrogate of the expensive solver. So these two models, one is coarse solver and the other one is DeepNet, are coupled using domain decomposition. And this work serves as a proof of concept that machine learning can accelerate multiscale modeling by orders of magnitude. So here, I'm going to introduce the idea of our framework. So let's consider a complex system where you have some Dirichlet boundary conditions and traction boundary conditions, and you can think this material is a kind of bizarre and strange, where you don't know for some region you don't know the constitutive model that's for example in here, and the only thing you can have the only thing you have can be acquired from experiments, and for some region these materials are undergoing fracture or cracks. And for some regions with higher strengths, so there could be some plastic deformation, and for some regions that you may have some microstructures that can be accurately captured by some molecular particle method, for example, molecular dynamics. So for the Y region I'm showing here, so we don't care too much about the behavior in this region. So we just take some coarse solver, for example, finite element, to give a coarser description of that. Oops, sorry. So the traditional way of investigating the mechanical behavior of this piece of material is to couple all of this solvers together with this finite elements and run this simulation at a very expensive cost. But in our framework, we would propose to use a much cheaper surrogate, DeepNet, as a surrogate to simulate the behavior of this particular regions. So philosophically, so you can use DeepNet to learn any of the system I'm listing here, including molecular dynamics, dissipated particle dynamics, DPD, or SPH, or paradynamics, or some nonlinear finite elements, linear finite elements, or even learning directly from data. So you can, once you collect some of the data offline, and then you can train your DeepNet, and then on the online stage, you can just do the plug and play game and run this multiscale coupling on the fly. So basically, this is the idea. So as I mentioned, step one is to train, is to find a powerful operator of these, a powerful surrogate of this systems. So what we take is DeepNet, which is developed by Lulu. So so I would like to mention, I think everybody can be very familiar with this model, but I just like to mention that the branch net input could be a function including boundary conditions of the system, or initial conditions or parameters of the system, and the trunk net input is a coordinate. So of course you can apply other types of neural operators such as FNO or coupled attention learning proposed by Paris. But we just adopted this DeepNet framework because of its flexibility, and we just chose this model as an example. So once you train the network, and it turns out you can, there's a lot of flexibility that you can couple the DeepNet with finite elements. So you can either choose overlapping or non-overlapping domain decomposition, as I'm showing right here. So in model, for model one, we typically take this as the coarse solver, or in this case is a finite element solver. For model two, we take this as our trained DeepNet. So you can, so here this in this region is an overlapping region, and or you can couple them in a non-overlapping decomposition. And it turns out it's also flexible on choosing types of boundary conditions when you couple this two model together. So here I'm showing you a schematic of model coupling with Robin type boundary conditions, which is a more general type of boundary conditions. And R1 and R2 are two coefficients in this Robin type boundary conditions. And by tuning this value, tuning these two parameters at different values, and you can achieve either Dirichlet type boundary conditions or Neumann. So I'm gonna take, so just bear with me now. So in this slides, I'm showing you a more detailed procedure of how to coupling these two models. So first, we start with some initializations of model one. So in this case would be U, as set U or traction as 0, and take that as the boundary conditions for the model one. And we send this, we pass this information into model one, and then we can calculate the U1 at n+1 step, traction related information T1 n+1 from model one. And then we pass this information into model two. And then using this information, we perform a forward propagation, and then get this U2 n+1 and T2 n+1 from model two. And based on that, we can update the boundary conditions or the Robin type boundary conditions H tilde here by combining the information collected from a model one and a model two. So we this equation shows the relaxations algorithm that we use to update the Robin type boundary conditions, where H1 indicates that this is this Robin boundary conditions is using the information collected from model one, and this H2 means that from model two. So H1 is defined as here. So, and then the next step is to determine if this if our simulation result has converged. If not, then we will proceed to the next iteration until the convergence criterion is achieved. Then we'll end our coupling. So is there any questions for this coupling steps? Well, if not, let me move into the examples. So in the first example, we considered to solve a Poisson equation in this square domain. So we decompose the computational domain into two overlapping domains. One is omega FEM, and the other one is omega NN. So you can see that the omega NN is bounded by this omega gamma 2. Oh, sorry. And omega FEM is bounded by gamma 0 and the gamma 1, which is in the inside. So this blue region are the DeepNet the DeepNet region, and these triangles are the region that I use for finite elements. We take the Dirichlet condition, Dirichlet boundary conditions at the interface, and the first step is, and this shows the coupling workflow. So first, we run our finite elements and pass some information into DeepNet. Here is the input of the DeepNet is model solution from the finite element on gamma 2. And then the output of the DeepNet, which here I'm showing right here, is model solution, which is on the inside. And then we perform this relaxation schemes and do the next iterations. So here I've summarized the procedure of our framework. So first, so here's how we train our network. So we first have we draw a mesh to this square domain, and then we sample the boundary conditions, some boundary conditions from Gaussian random fields, and then we use this sampled boundary conditions to solve the finite elements at the given boundary conditions, and then we collect the data as the training data. Once we train the data, and then we can do the plug and play game by coupling this DeepNet, the trained DeepNet with a finite element, and then we will have the system solution at certain boundary conditions. That's how we do this coupling. So here I'm showing some training results. So you can see that the MSE of the training is at 1.6 times 10 to the power minus 6, and the network learned the system well with MSE testing at 1.9 times 10 to the power minus 6.
Minglang, why don't you use a cursor to show, because we have so many things on the slide, we don't know what you're talking about.
Okay, so here.
And may I ask a small question?
Yeah.
So this is Adar from Brown, office next to you. So one, just to make sure I understand correctly, so the middle rectangle, right, is outside the domain, like it's a domain that has some. What is the rectangle that is inside the omega NN?
Oh yeah, so this actually is void. So there's no
void.
Yeah, there's no elements there.
Right, and there's some boundary condition between that void and the actual domain that you're trying to approximate, and then the DeepNet is overlapping but still capturing the boundary. Yeah, okay, I think I got it. Thank you.
Oh, okay.
Can I ask another question while you have that slide up? So the you've made a choice to set it up so that you can punch out this domain, and now you're training it by sampling from the trace space, like the set of boundary conditions for it.
Mm-hmm.
Is there a way though, in a larger, like in a kind of in a system of systems setting, can you train this with the coupling? Like, could you train the whole coupled system at once? Could you do like backprop through the through this Robin boundary condition, or does this force you to do everything offline? Like, you need to know what the correct boundary conditions are to sample.
So let me repeat your question again. So you're asking if I can do this coupling, or if I can train this coupling framework on the fly. Is that what you're asking?
Well, you're assuming that you know what boundary conditions to sample, the way that you have it set up.
Yeah.
Right. So it may be that this is like some small subsystem embedded in a very, very large system. And you only need to sample in some narrow range.
Yeah.
Do you know what I mean? So I guess I'm trying to understand whether the full coupled workflow is differentiable. Like, you can do backprop through the whole thing. I understand that you've chosen to do it so that you just do it through the boundary conditions in this offline phase.
Well, the whole framework is differentiable. You mean with respect to what? So
well, when you look at the coupled system of the FEM plus DeepNet, and you want to know the branch and the trunk hyperparameters.
Yep.
Right. Can you train that whole thing in a monolithic way? Or does this Robin coupling force you to do it? Because it's iterative, right? I'm just curious if that prevents you from being able to backprop through the whole coupled system.
Oh yeah, so I would say that's an interesting question to think about. So I'm not sure the answer now, but I'm going to show you. But I can tell you that here we actually take the backward automatic differentiation of this with respect to our input to get the gradients at the boundary. So this, at least for the depot net, is differentiable. So I'm not sure like if we can do this for the coupling framework. So I think that's yeah, that's, and I guess you must have to do that. You must have yeah, the finite element solver must have the automatic automatic differentiation feature in that, so that you can make this whole framework differentiable.
Yeah. Anyway, just curious. Sorry to interrupt.
Oh, no worries, no worries. Thanks. Okay, so here I'm presenting some of this coupling results. So I'm presenting this true solution from finite elements on the left for the omega FEM domain and also omega NN domain. And then I'm presenting the coupling result in the middle. As you can see that this finite elements solver compared with this true solutions have a match very well. And also this is, we can see a consistency between this NN prediction and also this true solutions with some minor errors at the boundary. I think these boundaries are caused by the interpolation of our finite element solver on the outside. So more quantitatively, I compare this solution at the two boundaries. One is at gamma 2 and the other one is at gamma 1 with the true solutions. And you can see that so the overall framework errors is down as low as 0.07% and 0.078% on gamma 1. In addition, we do a little bit of parametric study, and we want to investigate if the boundary conditions can affect the convergence rate. So we first tune this theta at different values of theta. Let me remind you, the theta is here, the relaxation parameters here, and it depends on and it really describes how much information I take from the finite element solver or the NN solver. So by tuning at the theta at different values, we can see that the model converges at different rate. And we observe that at theta, when theta equals 0.075, they converge as fastest. And then we study if we can apply this Dirichlet-Atkin method to dynamically update the value of theta based on our simulation result. And it turns out it can improve a little bit the overall the framework converge at 10 steps. And then we decided to try the Robin boundary conditions, and we found that if we apply Robin type boundary conditions with dynamic updated theta, then we can converge within 3 steps. So it's I would say it's very intuitive, because in Robin condition you not only have the information from the solution itself, but also its derivatives. So there will be more information that is formed into this framework, so naturally it will converge faster. And then I've tested the model generalization ability. So as I mentioned, I sampled this boundary conditions from a Gaussian random field. So this alpha parameter controls the smoothness of our samples. When alpha getting larger, and it means that our curves are smoother, and when alpha getting smaller, it means that we have more oscillations on the boundary. So, and I sampled different boundary conditions at this different alpha, and then perform our coupling framework, and this is a relative error. This is a result we have. So I'm presenting the relative error versus the alpha value. So we can see that if we use alpha larger than 5, and then it can extrapolate or generalize very well. But if the alpha, if we use alpha smaller than 5, then it's not going to have a very good result. And then I investigate the number of training cases that we need to train the neural networks in order to have a good performance. So we found that basically, if you use more than 300 training cases, then you can solve this system very well. So yeah, so this is what we found from this parametric study. Next, we want to see if we can apply our framework to a dynamic problems. So then we take a very simple heat equations as example. So this is a 1D heat equations. So I'm showing the spatial and temporal domains. So we decompose this overall this computational domain into 2 non-overlapping domains. So omega NN and omega FEM. And the gamma here is the boundary between these 2 domains. So in FEM, we just want to predict the 1 step forward based on the information we have, and then use this information we have as the input for the DeepNet, and then we can predict the spatial derivative of this on this NN domain. So I think this has advantage when you do extrapolation, because, well, traditionally, if you want to predict this on a system in the temporal spatial domain, you're gonna put a coordinate as well as time into the as the input of the trunk net, and then, well, the network will lose its performance when the time is getting larger than your training region. But here we just take, if we rewrite the system into a semi-discrete form, right, as I'm showing you right here, and we use the prediction from DeepNet as the spatial derivative, then you can just do you can use this backward Euler and get this system equation and do this time stepping in this way. So in this way, you don't have to put the time as the input of your trunk net. Then it will give you more, it will guarantee the performance of on extrapolation. So this is a coupling framework for solving dynamic problems. So the inside is exactly the same as what I was showing previously. And the only difference is that we have an outer loop, right, showing right here. So K is the time step, N is the iteration steps. So when the solution is converged at a certain time step, then we terminate the inner loop, and then we move out and move toward the next time step, and then we do the inner loop again until the overall solution, until we reach at the last time step. So here I'm presenting some training results for the MSc training. We have a comparable like MSc on training and the testing. And then for the coupling, as you can see that the NM prediction match the true solution very well at a relatively long time range. And notice that we only use the information training data from that is sampled from 0 to 1 second as our training data. And then beyond 1 second, it's all about the model extrapolation. So as you can see right here, the model converged to its solution very, very quickly at each time step. Okay. So next, we're going to look some mechanical problems. So this is our computational setup for example 3. So let's consider again a square domain. We have some tractions on the top. We fix the displacement at the bottom, and we have a void in the middle. So because for the region which is close to the void, the strain will be higher. So this will cause some plastic deformation. So in order to simulate this kind of plastic deformation, what you can do is to decompose this overall domain into two regions. One is omega FEM, and the other one is domain omega NN, or omega plastic region. So traditionally, you're gonna cover, you're gonna couple these two regions together concurrently, which can be very tedious on writing the code, or it's gonna be expensive when you go to 3Ds. But here we just use our network to learn the mechanical behavior on the inside, and then we pass the information of traction and displacement at the interface so that we can dynamically update our system until it's converged. So yeah, so what I'm showing here is based on what we predict, which is stress fields of the inside. We can actually get the equivalent plastic strain and the inside, which is more informative for this types of elastoplasticity problem. So here I'm showing some results from our coupling from a coupling framework. So I'm comparing, and notice that in the finite element region, we just use a linear finite element to do the simulation, whereas on the inside, we have this neural network predicted epsilon bar. So both of these stress fields shows a good result. So we also plot the displacement and traction at the interface. So we can see that these two model matches very well for the true solution and also the neural network and finite element. And the overall framework, the framework converge at the fourth or third steps, which can give you a very fast convergence. And next, for the system, it's a little bit different from the previous ones. So here we want to learn hyperelasticity from a particle solver, SPH. So at the inside, we use SPH, which is a particle method, to simulate the mechanical behavior. And on the outside, we just use a finite element. And we train our network to learn the mechanical behavior informed by this SPH solver, and do the same coupling things and see if we can get a good result. So this is basically the idea. So we take, so the constitutive here is anisotropic hyperelastic material proposed by this HGO model. So we take this model as compressive so that we can avoid some incompressibility issues when you do the implementations. But anyways, so again, I'm presenting some of this training result and also the testing results. All of the results are showing that the network can learn on the mechanical behavior very well. So I'm comparing the displacement in the vertical direction for the FEM, and also I'm comparing the P22, which is a Piola-Kirchhoff stress in the vertical direction from our network. So you can see that the overall predictions are very well, except some of this discrepancy at the inner boundary. And then we study the impact of a Robin boundary on the convergence rate. So we found that when R equals 0.25, and it can converge fastest. So, which is a little bit faster than the Neumann boundary types condition. And notice that if we do this finite element SPH coupling, and then it's going to take 4 hours for a single iteration. Whereas if we replace the SPH by a DeepNet, then the overall framework can be achieved within 1 second. So this is so we are really seeing a magnitude of orders improvements on the computational efficiency. As a conclusion,
another question about
sure.
the boundary conditions. So to couple to the finite element code, right, you need to evaluate the traction, like you need to integrate the weak form. And so depending on your branch and your trunk net, it's going to be some sort of neural network that you're evaluating, which you don't have an exact quadrature rule for. So how are you, and this would be exacerbated by SPH, where boundary conditions are really tricky in general. So what's your strategy? Are you just using like lots and lots of quadrature points and hope that can you explain a little bit about what that looks like?
This is a little bit, this is a very good question. So it's a little bit tricky on doing this type of like the or interpolation. So especially when you have this particle system. So what I did was to use the built-in, built-in features of Python and do this linear interpolations. And it turns out it works well. But I think for a more complex system, I would suggest to go with a non-overlapping region, because you're going to have more information at the interface. So that the particle will be there will be more particles around at the interface, instead of just using particle information from one side.
How do you sample? So your strategy was to sample a Gaussian random field to learn the boundary conditions, right? But for SPH, you need boundary conditions along a full, it's a volumetric collar around the region.
Oh, so I like to mention that how we train this, how we do this data acquisition. So basically, we replace this finite element region with particles when we do the training. So we just sample the boundary conditions on the top, and then we perform SPH for this all particle system. And then we extract some of the information at the interface as training data for the DeepNet, and then we do the coupling. So basically, I did a full-scale simulation of SPH at the training stage, not just the do this sampling at the interface. I'm not sure if I made this clear. So.
Okay, thank you.
Yeah, but the point is coupling this particle and the continuum level regarding this and the boundary conditions definitely can be tricky for sometimes. So in this work, we developed a machine learning framework for multiscale modeling, and it provides a demonstration that neural operator are capable of coupling standard numerical solvers, and it can accelerate the multiscale modeling by orders of magnitude. And in the future, we're going to look into a more complicated system in 3D, maybe has some local fracture, or some micro structures. So with that, I would like to thank my advisor and my collaborators and funding resource.
Some data, thanks Minglang. Some data. I want to show, especially Nat, who is from Sandia. We have the same thing for time. So I want Vivek or Raj to show what we have done with Sandia project, where we interface Memphis with DeepONet and see some of the gains. In other words, this whole thing is about accelerating existing solvers, right? With so Vivek, can you share the screen? And then you can ask questions to both of them.
Yeah. Yes.
Okay, Vivek, go for it.
Yes. Can you see the screen?
Yep.
Yep. So this was we were justifying one of the reviewer questions, so that how to make Memphis solver for microstructure, how to make it fast by using the DeepONet.
So the project is evolution of microstructure, what we were talking earlier when Mingdao asked actually about microstructure. Yeah. Okay.
Yes. So we have a 2D microstructure that is evolving in time, that is governed by the Cahn-Hilliard equation. So we are trying to learn a data-driven surrogate model. So we have a first step of learning a low-dimensional representation using a convolutional autoencoder. That is the first step, training of the autoencoder. Then in the latent manifold, we learn the dynamics using a DeepONet. And using the pre-trained transpose convolution decoder, we'll remap to the primitive space and we'll reobtain the actual microstructure. So this is the full framework. So one of the reviewers' comment was, we initially did only for 10 time steps using DeepONet. Yes. So one of the reviewers' comment is how to utilize it further. So we came up with this approach in which for the first 30 time step, of course, we'll use Memphis numerical solver. From
30 time units, because 30 times means 500,000 time steps per unit, right?
Correct. Yes. So firstly, one time unit for the DeepONet corresponds to 500,000 time steps for the numerical solver, Memphis numerical solver.
So we're talking about a lot of expense. You're breaking the bank.
Yes. So first 30, of course, we'll do with Memphis numerical solver. But from 30 to 40, we have a pre-trained, we have already trained autoencoder DeepONet framework. So we suddenly leap forward in time, accelerate in time. Then 40 to 60, again, we'll use the Memphis. 60 to 70, we leap in time. Again, 70 to 90, Memphis. 90 to 100, we leap in time. So in real time, we can use a already trained DeepONet from 30 to 40, 60 to 70, and 90 to 100. So we can avoid the training time. It's just the inference time, which is very fast for DeepONet models. And yep, so this is the proposed framework.
So in this to integrate DeepONet,
can I ask, so why do you, I'm missing something. Why do you need to go back to Memphis and take steps and then do DeepONet?
Because you cannot extrapolate forever. This is extrapolation. 30 to 40, you extrapolate for that long. We cannot extrapolate. No neural networks that can extrapolate. So
I understand. So this is like a multi-scale.
Yeah.
I understand. Yeah.
This is, I think you guys missed the point. This is the same idea that Minglang was doing, but in space. Now this is in time, right?
Yes.
So you can basically do so much, but especially in time, you cannot extrapolate too much. So
one more.
Go ahead, Vivek.
One more thing I want to point out is each realization itself is a time series. We are trying to extrapolate multiple time series. There are multiple realizations. It's not just one realization. We are showing only one realization, but in reality, we have so many different realizations. So yes.
So to integrate DeepONet with Memphis, what we did, we wrote a subroutine for Memphis where it will take the output from the DeepONet and then propagate for that, like whatever the time we choose here, just like for 10 steps. So this is like 500,000 into 10 steps. So and DeepONet takes only 1 second to predict from 30 to 40. And for Memphis, it takes like 90 minutes to do the same simulation. That too on 2 nodes with 16 core each node, like 32 core. So for 1 core, if you say this is like just 32 into 90 minutes. So that much expensive the Memphis solver is for that period. So there are some results. We just want to show that.
Yes. And the time mentioned is for just one realization. Okay. One realization. Yep. So here is the result of how the Memphis is able to correct the prediction coming from DeepONet. And as Memphis takes the input from the DeepONet at the 40th time unit, it is going ahead from 40 to 60 using the Memphis. And here is a video of how it happens. Yep.
So left image is a true microstructure. Suppose it was just coming from the numerical solver. And this right one is the reconstruct microstructure with starting solution coming out of the DeepNet. And so you can see that it's automatically correcting the solution. So it is, as it moves, it's correcting the course for the trajectory, that how it should look like. It's exactly like we're sampling it from Memphis. So
yes, and
this is just a collage.
Yeah, just a moment. I'll just zoom in a bit. Just a moment. Yeah. Yep. So just to put things in perspective, so for one realization, it took 90 minutes to go from 40th time unit to 60th time unit in the Memphis. Then, as we said before, using the pre-trained DeepNet, in the inference stage, we leap in time from 60 to 70 in just 2 seconds. Then again, 90 minutes from 70 to 90, leap in time with 2 seconds. From again, 100 to 105. Yes, this is 105. Hope you can see. Yeah, it just take 22 minutes. So, yeah, so that's it. Thank you.
And the accuracy is same for training plus data.
Is it clear? Or I don't know if Panos is also there, because we're just doing something, talking about how we can actually use DeepNet neural operators to accelerate existing solvers, right, in the labs, for example.
Right. This makes a lot of sense. That, and this is similar to the last talk in the spatial domain. The Robin boundary condition is really a question of the Dirichlet and Neumann map. It's a way to approximate that. And you could also do it like a Mortar method, where you actually constrain it so that you have a Lagrange multiplier. So Eric Sears' time domain multi-grid stuff looks like this, but with a constraint. So that might be another framework that would be maybe more rigorous, that you could yeah, the idea makes sense. Have you done this on Remy?
Yes.
This is Remy. This is Remy data.
This is for Remy. I see.
So the paper, they like the paper because we could extrapolate. We could do much better than them, and the paper was submitted to Nature Computational Materials.
Right.
One of the reviewers had this question. So because what is it for? I mean, that's the question. Like, because in time you cannot extrapolate in this chaotic dynamics. You cannot extrapolate for a long time. But how long? So they show that basically, look, you can train for 3 hours, let's say from 1 to 30. Then you can extrapolate a little bit and you're very accurate. But here they are very ambitious. They say, well, I'm going to extrapolate 1/3 of the training period, which is too long. But of course, you don't get the accuracy. But very quickly, Memphis corrects the trajectory.
I see.
So
it's a lot like Kevrakidis's, like the projected.
Yeah, exactly. Similar idea. That you inject data, and then you. But also here, most importantly, you can actually do long time integration efficiently. So
right, exactly.
At the end, what the lab is, Remy, instead of doing like a week of simulations, he could do probably 1 afternoon of a simulation.
But there's like what's the bottleneck law from parallel computing? Is it Amdahl's law? There's the thing
that's paralyzed in space only. So after a certain time, it will not scale anymore. So
right, exactly. This will only give you as much scaling as you can remove in the orange region, for example. Yeah. So how do you have a sense of how big that ratio is? Is that
yes,
its ratio is 1,000 almost, like
if DeepNet Memphis had gone from 30 to 40, it would have taken like 45 minutes, but DeepNet is taking 2 seconds, so the speed up is close to 1,000.
Yeah, but within the green regions only, right?
Yes,
so
in the regions only.
So you can only accelerate this as much as you like. Imagine DeepNet makes it free, right? It doesn't accelerate the orange region. So at the end of the day, that might be like an 80%.
Yeah. So we have 10, 30 by out of, so we are getting 30% acceleration.
Yeah. Also that in that case, this is just for one realization. Like that, we have 1,000 realizations. So like we can train DeepNet for all the realization.
Same DeepNet can be used for all the realization.
So, but for Memphis, you have to start the simulation from first.
Right.
There is no.
But the point's clear, right? Like as you've drawn the figure, that would be like a 20%.
Yes.
Yeah. 20 to 30.
Reduction in cost, right? But it's not like, even though the green area is very, very fast, you're not cutting the overall simulation down by more than half.
No.
Right.
Here
Is that right,
30%,
George?
yeah.
Do I
For
understand
whole
that?
pipeline, it's 30%.
Yeah. Anyway, yeah. The point taken. Yeah. This is interesting.
Thank you.
Thank you.
Some data, maybe we can go back to Minglang's and people may ask him questions. Sorry to add.
So one question, George, if it's okay, this is Shomnath.
Yeah, hi Shomnath.
I'm sorry, I was in another meeting and I could only catch the tail end of this presentation.
Okay.
Looks like a very interesting method. My question is, when you have very strongly path or history dependent phenomena, how does this method perform both in terms of the time scaling and multi-scaling in space and time? Because that obviously affects, even the training data that you have.
Yeah, sure. Minglang, you can take this question for your case. Like if you had a hysteresis, for example, in a or viscoelastic material, how would you do that? What would you?
So I think this is a very challenging problem, especially when you have this strongly time-dependent behavior. So what I would suggest to do to improve the accuracy is that you train this network as accurate as possible and use offline, yeah, of course, and take a smaller time step in order to restrain the temporal errors when you do the time stepping. And I would say the error may come from both of this side. One is on the training and the other one is on the temporal. And of course, and there may be other error sources, but that would need
the question would be, how would you even gauge that error? Yes, I know if you can figure out that error, you probably can train accordingly. What the challenge is for these very strongly history dependent and path dependent. Path means you're going to the same end state, but taking very different paths.
Yeah.
And the result is going to be quite different, right? So the question is, how would you even qualify an error, right? Because that is not that trivial.
So can I add to that?
Sure.
Yeah. So in one of our problems where we are dealing the climate data, they have a lot of memory dependent the field variables. So for that we integrated DeepNet with LSTM. So as far as memory is concerned, we can incorporate in the training. So, but for this is the problem which we showed here for time integration. We did not use any LSTM, but yes, as far as memory is concerned, we can incorporate in the training, and then we can check how far we are off from the actual. So, but yeah,
so that's the answer. So DeepNet can have multiple branches. So an RNN type, LSTM is a cheaper version of an RNN, a recurrent neural network, will incorporate time history. So the idea is not to use one monolithic architecture for the domain. It depends on the, but RNN would be exactly what Raj mentioned, because we are doing very coarse simulations. For example, in the climate, 3 kilometers instead of 100 kilometers instead of 3 kilometers per direction. You have this, when you coarse grain, you have these history effects. It does, in other words, you know that, right? From the Morris-Wanswyk formulation, when you coarse grain, you have history effects. So you have to take that into account to correct the path, actually, like you said. So that was done with an LSTM, which is a stable version of RNN.
Okay. All right. Thank you.
I would like to add on that point. So,
sorry, Somnath, sorry. It's not to de-emphasize that this is really a difficult problem, okay? but it's
no,
not.
No. No, I know. No, what you the steps you are taking are good steps. I just trying to see where one needs to put more focus on. If you have to solve some of these problems. For example, I'm very, very interested in fatigue, right? Fatigue actually has both extremely localized phenomena, which is extremely path dependent and depends on the local states, as well as there is a time history there, right? Because we really have to move fast when things are benign, but once a fatigue crack starts and then propagates, I mean, you suddenly have to, it's like pulling the brakes and follow the cracks, right? So it becomes a completely different time scale problem there. So I'm coming at it from that point of view, but I see some very good possibilities. That was the genesis of my question, actually. Okay. Thank you.
Len, you would want to add something you mentioned?
Oh yeah, so this from technical perspective. So because essentially DeepNet learns the function, the mapping between functions. So as you mentioned that the state can be also incorporated in either the branch net or the trunk net. So that can be taken as some of this input to reflect the current state, either you whether you have the same displacement or traction fields or not. So that could be also incorporate when you do the offline training. So that's
okay.
Yeah.
Okay. All right. Good. Thank you.
Do we have more questions for Minglang?
Yeah, I have a question.
Yes,
so this is a very nice work. I have a question. For example, the example for your learning hyperelasticity. This model actually has it's actually anisotropic property. So when you actually, and it's actually normally they deform with finite deformation, and it will involve rotation of the fibers because it's not a uniform structure. So how do you handle this? Have you yet do something to track the? I mean basically the material baseline coordinates will rotate while you deform. Have you picked that into account yet?
I think we take the Lagrangian formulation, which is to fix the reference state, and we just get the displacement on the top of that. So which is we can avoid this Eulerian description.
I see. You everything refer back to the original.
Yes.
Okay, that's how you solve that. Okay.
Yeah.
Okay.
And based on that, we can just have the deformation gradient, and based on if we have local deformation gradient, then we have everything.
But still, you still need to have it's still an anisotropic behavior, so you still need a
right. So in the model, I'm gonna show this again. So in the model we take here. So as you mentioned, the fiber orientations is encoded in this E, which has something to do with the fourth invariance in the continuum mechanics. So it really and the E is a function of both the red Cauchy green and also the fiber orientation when it at its reference configuration. So if we know the fiber orientation a priori, and plus we know the local deformation gradient, then we can have this. It's no problem. It's not a problem. Then we can predict the local stresses.
I see. Okay.
Yeah, it really depends on what equations or constitutive model that you're looking at.
Okay, the other question is actually looks like DeepNet is is almost like capable of replacing finite element. In what sense it's can be a surrogate to a finite element simulation?
Well,
you learned that complicated operator.
No.
Not yet. Okay.
No, so it's a very I would say it's it serves as a complement of finite elements, so it's not going to replace this finite element solver. So because the types of
Minglang is referring to the fact that you were changing the nonlinear finite element with surrogate. So the DeepNet, which was replicating the action of a nonlinear finite element solver, not replacing it from the books.
Oh no! I'm not saying replacing, but it's like in the forward sense, you put in some boundary conditions and some loading, and they will behave as if you're doing a finite element simulation.
That's correct. I just want to talk to Somnath before Somnath Minglang, who gave the presentation, actually we kick him off, so I kick him out, so he will come to Johns Hopkins in August. So he will be at the in the group of Natalia, so he will be very close to you, not the same campus maybe, but maybe he didn't hear.
Anyways.
Do we have more questions from Minglang?
Hello. Can I ask you some questions, Minglang? I'm Ting Wei. Yeah. Can you show me your slides? Okay. So I have 2 or 3 questions. The first one is a general question about the domain decomposition. So you said there are 2 ways to do the domain decomposition. One is non-overlapping, and the other one is overlapping. Is it like standard way to use the Neumann boundary condition for the non-overlapping and Dirichlet boundary condition for the overlapping, or
well, you can, well, these are 2 independent things, so you can either choose you can choose overlapping with Robin or Dirichlet, or you can choose non-overlapping with a Neumann or Robin. So it's flexible, I would say.
Yeah. Then why do you choose? I mean, what's the reason for choosing those boundary conditions?
Oh yeah. So here let's take this elastoplastic, for example. So so in this case, it goes back to the property of this equation. So if I impose some traction, if I take the traction as the input of a DeepNet, then it's not gonna then the solution will not converge, I would say, because in this linear, because of the accuracy of the finite element that we choose. Because essentially, if you want to calculate the traction, it's essentially is a derivative of this displacement field with respect to some direction. And so if the accuracy of your FEM is not high enough, then you're going to have some very noisy and fluctuating field that can damage the convergence of the overall convergence. So here we take the displacement as the input for the DeepNet. So
okay,
yeah, it's a really problem dependent answer, but yeah, that's a very good answer.
I see. So actually, in your first example, I think you have the overlapping domain, and then okay, and then you use the boundary condition on the boundary only, I'm thinking about whether you can make use of more information on the overlapping part instead of on the boundary only.
Yeah, of course. If it's a non-local method, if it's a non-local method, so you're gonna use some information more than just on the boundary. So I would say that's doable. But in our case, we just want to sort of replace this finite element by a depot net. Then that's the reason why we set this. We only use the information on the boundary as the input of our network.
Okay, I see.
Yeah. And actually, here, as I'm showing here, the Robin type boundary condition. So we not only use solution, but also its derivative, because that's what he needed in the Robin. So.
Okay, and another question is about the heat equation. I think you have mentioned the reason why you used time discretization on the depot net, but sorry, I missed that part. So can you explain again?
Yeah, so let me do the annotation, because traditionally, if you want to do predict this time-dependent behavior, you're gonna have X and T to the trunk net, right? So when T is greater than the training region, maybe T train, and then your performance is not going to be good.
I see.
Yeah, I'm just replacing this with some backward Euler or some numericals time stepping method.
I see. Then can we like do time as input, but when you evaluate the depot net, you only have time less than the training time.
Time as input and what?
Yeah, when you do the evaluation, because you said the reason why you do the time discretization is when you do the evaluation, when time is too big, the error would be large. So I'm thinking whether you can still like do your time step, but you have the time delta t as the input.
Oh yes, definitely.
Yeah, in that way, I think it will be more flexible because you don't need to fix the time delta t. So
I agree.
Yeah, and another question is so here you replace finite element by depot net. Then my question is, can you replace also the outside finite element by another depot net, or?
Yeah, I agree. So well, of course, then you're gonna train the outside, but our idea is that the outside solver is not very expensive. It's affordable. Okay. So we just if you compare this microscale solver and the computation efficiency of the microscale solver and the macro scale solver, so you're gonna see that most of the time are taken by this fine scale solver. So we just tackle the main cost of time by replacing it with a depot net. Then the rest of the time are negligible. So that's what we assume. But of course, you can try to couple two depot nets.
Okay.
Yeah.
Thank you. And can I ask one question about the other part? The second part. Sorry, after your presentation, the other
you wanted to ask questions to Vivek and Raj?
Yeah.
So yeah, they are there in the audience.
Yes,
Vivek,
just a second. Let me share my screen.
Thank you. Yeah, because I'm thinking about the last page of the slides. About the numerical results, the last page.
This one?
Yeah. And I saw in the output of the depot net, you have some boundary error
Correct.
I don't know, when you see the third line, you have
yes, yes, I'll tell that. So the image resolution is 512 by 512. So what we did was we split each image into 4 parts.
Okay.
Right? So we'll have a 256. There will be 4 256 by 256 images. And we consider them as independent realization while training the deep-neural, while training the surrogate data-driven model. So that is why there is an inconsistency at the boundaries.
I see. So you solve part by part, right?
Yes, it's space. Yes, because the number of realizations available to us was limited, which is just 400. So we had to increase the number of available realizations. We did that by considering each realization as 4 different realizations, or each time series, or each dynamical realization as 4 different time evolutions.
Okay. Gotcha.
So therefore, at the end of deep neural prediction, there will be some inconsistency across the border, but that will be taken care by the Memphis, which evolves for the next 20 time units.
I see.
Yep.
Do you do that for the performance? I mean, to fasten the...
We mainly felt that because else the number of training realizations will be very less. To increase the number of realizations with respect to the number of trainable parameters.
Okay.
Yes.
Thank you.
Thank you.
That's all my questions. Thanks.
Thank you.
Do we have more questions from Minglang, Vivek, and Raj? So if there are no more questions, let's thank all our speakers for the wonderful talks they gave us. And with that, we come to an end of our seminar today. Have a great and a happy weekend ahead. Thank you.